So what we can see here is that here we have the Arduino that's hooked up to this circuit, and here's the MOSFET, and here's the resistive load I am switching right now, and it's just using a integrated Darlington transistor pair with a pulling down P channel MOSFET. It can go up to, it's currently switching at, well, it was switching at, let me fix this quickly. So, okay, excuse me, it is switching at, again it was switching. It's not very stable because the loads are, they're getting loose, the capacitance is discharging, and it's simply not a stable circuit right now. But as you can see here, 270 milliamps in idle, it's currently not doing anything, and I will leave it here. Let me switch off the lights. Okay, now you can see, and if I turn on the MOSFET, it's still the same, but I can assure you that there's almost 2 amps of switching, pushing and pulling, 2 amps. But there's something very important going on, which I will show you when the light comes on. So what is very important in this setup right now is that, as you can see, it's still on, still in idle current, but what's the most important thing is that there are 2 bypass capacitors, and currently the transistors are taking the voltage from these very low equivalent series resistance electrolytic capacitors, because that's what they're known for, and they can discharge huge amounts of current without even affecting anything else. So it's currently taking the voltage from these capacitors, and it's doing that at around 2 amp per, let's say, 5 or 2 microseconds, which is absolutely nothing, but you can barely see anything. It's not taking extra load or anything. It's just charging at 2 amps, and my power supply, which I am using a wall adapter, is only rated for 1 amp. So as you can see, I am switching at 2 amps with an input current of 1 amp. It's almost impossible, but it's thanks to these electrolytic capacitors, which can store the energy and then release it at whenever you want it. So here's the proof, so that you know I'm not bullshitting. And if we can take a look, I'm not sure if I can zoom in. As you can see, it's almost 100 kilohertz, 99.9 kilohertz. So you can imagine what kind of speed this thing is operating at. And let's take a look at the rise time. as you can see, it's extremely low. As you can see, it's 24 nanoseconds, which is extremely fast. It's unimaginably fast. But now let's take a look at the fall time. And also this at 30 nanoseconds, which is very, very fast. If I can achieve this with the power supply, I can achieve great amounts of efficiencies and power. So that's very promising. It took me a while to get this all to work, but I finally done it. I even made an episode before which completely failed, but it's nice when things work out. So what I'm going to do next is I'm going to design the whole circuitry and actually build the power supply, and then we can charge some capacitors, and when capacitors are charged, bad things will happen, and you know what kind of bad things will happen. But for now I need to design the whole control circuitry and all that kind of stuff, so that's for another episode. And perhaps in the distant future I will do some tests with this kind of gate driver and then see what the boundaries are, if I can achieve something like 5 megahertz like I could with the Arduino. But it's quite an interesting test, but not for now. I think I will show you a different problem with this kind of setup, but it's a problem which cannot be fixed. Let's take a look. So what I have done is that I have attached a second probe to the signal coming from the Arduino, and we'll see a big problem, or well, if you can work around it, I don't think it's a big problem. But as you can see, there is a slight phase shift, and if you are going to use, like me, a phase shift converter which is entirely based on shifting phases, this will be a problem because there's already a passive phase shift, and it's about 200 to 300 nanoseconds, which is a lot more than the rise and fall time, and it's definitely noticeable when you also zoom out. As you can see, it's very noticeable, but there's no way to work around it. You'll need a specific gate driver, integrated circuits for this, and I'll research that some more, but I don't think that's required. I'll just have to work around this problem and take it into account when programming. So that was all for now. I hope you enjoyed this video. If you did, then please subscribe and like this video, because then I'll know what people like to see and what they don't like to see. I hope you like to see this, because it's very interesting and you can learn a lot about this and possibly make your own stuff. But that's everything for now, and maybe this week I will post a video about testing this stuff out and see what the boundaries are of the switching frequency. And it's a fun experiment to do, nothing else. But maybe I'll even make another video this Friday. Not sure yet, but I'll see you soon enough. What I forgot to demonstrate was the floating problem which occurs at the gate from the MOSFET. And if I can turn the circuit on, and let's hope it doesn't turn off anymore, because this circuit is very unstable. And it's currently being pulled down by the probe of the oscilloscope. Very funny. And let's turn on the circuit again. Okay. As you can see, LEDs on. And what happens if I disconnect the signal from the gate? Turns off. But as you can see, it stays on. The signal is here. Right here. This is called floating. Currently the MOSFET gate is floating at the point where the MOSFET simply is on. It's charged, the gate is charged. And this is very occurring at high side switching, which is problematic because if the other MOSFET turns on, you have a direct short circuit. So how do you fix this? You use a pull down resistor. It simply pulls the remaining charge at the gate and it then discharges that gate to ground. So let's see what happens. You see that? That was the exact characteristics of a capacitor discharging. That was a very good demonstration. If you put the signal back, it still won't go on because the bypass capacitor is fucked again. Should really fix this. It's very annoying. And now we are going to put the pull down resistor in the circuit and we are going to disconnect the signal. Then we reconnect it and it stays off. Last time it turned on again. Could be the damn capacitor again. So there. Stays on.